In this lesson, we're going to look at electrolysis and Faraday's law, which is quantitative electrolysis. When we're dealing with electrolysis, we are using electrolytic cells, which are different from galvanic cells. The galvanic cells that we've been looking at so far have resulted from spontaneous reactions where the electrons naturally flow from a higher potential to a lower potential. In an electrolytic cell, we're going to use the non-spontaneous reaction, and it's going to require energy. So rather than like water flowing down a hill, we're basically going to be pumping water up the hill. Okay, so we're going to be looking at the reverse reaction that involves an external source of electricity being used in order to force the reaction to take place. Okay, so let's look at some basic differences of a galvanic cell to an electrolytic cell using our original Daniell cell. Okay, and in a galvanic cell, when we've got zinc and copper reacting with one another, the zinc is more likely to be oxidized while the copper is likely to be reduced. If we were to prepare an electrolytic cell of this reaction, the reverse reaction would be occurring, where we are going to force the electrons to be lost from the copper and be pushed towards the zinc cell. So a galvanic cell is spontaneous, it occurs naturally, while an electrolytic cell is non-spontaneous. So in a galvanic cell, we've got chemical energy and we're converting it into electrical energy. In an electrolytic cell, we're applying electrical energy to convert it to chemical energy. Okay, the anode and the cathode are the opposite. So in the galvanic cell here, the anode is zinc, and the anode is where the electrons are being generated, so it has a negative charge, and they're being consumed at the cathode, so it has a positive charge. The opposite is true in an electrolytic cell. The anode is positive, okay, because the electrons are being drawn away from there, okay, and they're being pushed towards the cathode, which is causing it to be a negative. Okay, and when we connect to the voltmeter, you'll kind of get the idea here with the positive and the negative. This is really a little bit of a sign convention. Okay, so you can see in this reaction, the oxidation is of the zinc and the reduction is of the copper. Okay, and in the galvanic cell, the E naught is positive 1.1 volts. Okay, so that's the cell potential, the difference in reduction potential of the two half cells. Okay, while in an electrolytic cell, we've got a negative 1.10 volts. And this is the amount of external voltage that's required in order to force the electrons to move in their unnatural direction. Now there's two kinds of electrolysis that we'll look at. We'll look at the electrolysis of a molten salt, which is a melted salt, and we'll also look at the electrolysis of aqueous solutions and how to decide the reactions that will occur there. When you've got electrolysis of a molten salt, what you are doing is the opposite of the forming the ionic compound. So for example, if you've got the electrolysis of sodium chloride, you've got sodium ions that are gaining an electron, and you've got the chlorine ions that are losing electrons, okay, which is the opposite of what they would like to be doing, so it makes sense that it would require energy in order to do this. Okay, so you've got sodium here gaining electrons. To get the overall cell reaction in this electrolysis, I needed to balance the electrons, hence the sodium having a 2 in front there. Okay, so if you want to look at the electrolysis of a molten salt, what you need to do is look at each of the ions, and they're going to react to form their elements. So if we want the electrolysis of magnesium iodide, we've got magnesium reacting magnesium ions reacting to form magnesium, and we've got iodine ions reacting to form iodine. And so you can see that the reaction that is occurring here is one where the magnesium is being reduced, okay, and the iodine is being oxidized. So the reaction that's occurring at the anode is the iodine reaction, and the reaction that's occurring at the cathode is the magnesium reaction. In the overall cell reaction, we didn't need to do anything in terms of balancing because the number of electrons transferred is equal. So we've got the overall reaction of 2 iodines plus magnesium going to magnesium and iodine. Okay, so that's all you have to do for the electrolysis of a molten salt. Okay, when we're looking at the electrolysis of an aqueous solution, okay, it is a little bit more complicated. So if you've got something like sodium chloride dissolved in water and you apply electricity to it and you want to know what the reactions are going to be, most likely, you've got competition because it's not just the ions that in the solution that could potentially oxidize or reduce, but water can be both oxidized or reduced. Okay, so this is the possible oxidation reaction for water. So water can be oxidized to produce oxygen and hydrogen ions, and its cell potential is 1.23. Okay, and water can also be reduced. So water can gain electrons and produce hydroxide and hydrogen with this particular cell potential. So when we've got ions in solution, we've got to look at all of the reactions that could potentially happen. So we've got to look at the competing oxidation and reduction of water to decide which one is going to occur. The one that's going to occur is the one that's going to require the lowest external voltage. Okay, so let's look at an example here. So we want to predict the products that would happen of the electrolysis of lithium bromide here. Okay, and I've got some updated steps in your notes. So what we want to do is list the relevant reactions. So the reaction for lithium ions in solution, okay, they could potentially gain electrons to form lithium. And what we're going to do is record the appropriate reduction potentials of this. Okay, so this is the potential reduction. Okay, the potential oxidation is that bromine ions can lose electrons to produce bromine. Okay, and the reduction potential of this is 1.07 volts. Okay, now this is our possible reduction, and this is a possible oxidation. So what we want to do is compare that to water's potential oxidation and reduction reactions. So for water, its reduction reaction, if it occurs, the voltage is negative 0.83. Okay, and that's the water where it's producing the hydroxide and the hydrogen. For the oxidation of water, the voltage is 1.23. So what we have here is a scenario where we've got two potential reduction reactions and 2 potential oxidation reactions. And what we want to happen is for the reactions to occur that will lead to the lowest overall external voltage to be required. Okay, so let's keep in mind that the Ecell is equal to whatever the reduction potential is at the cathode minus the reduction potential at the anode. So for our choice of reduction potential, we want the value that is the least negative or the largest. Okay? Because remember, we want the Ecell overall to be as close to 0 as possible. Okay? So for this part here, okay, we have a choice between negative 3.05 or negative 0.83. Okay? This one, okay, which is larger, is going to lead to a Ecell that's closer to 0. In terms of the oxidation, it's being subtracted. Okay, so we actually want to choose the smallest one, okay, because if we subtract 1.23, okay, it's going to lead to it being even more negative. Okay, so the ones of choice are the water is going to be reduced and the bromine is going to be oxidized. Okay, so what that leads to is the water being reduced, so this is the reaction for the reduction of water, and the bromine is going to be oxidized. Okay, so this is the reaction for the bromine. And so overall, this is the reaction that's going to occur for the electrolysis of lithium bromide. And the lithium will simply be a spectator ion. It won't be produced. Okay? Which is also kind of helpful, because if you think about what would happen if lithium were produced in this reaction, lithium is reactive, okay, and it would actually react with the water as it's being produced. Okay, so this is a possible reaction question where it just will say a solution of something is electrolyzed, and the process that we just went through is the process that you need to go through. So if you've got potassium iodide being iodized, you've got the 2 half reactions. Okay, this is your reduction choice and your oxidation choice. Okay, and you want to look at the reduction potentials of these. So the reduction potential for potassium is negative 2.93, and the reduction potential for iodine is positive 0.53. Compared to water, for water the reduction is 0.83, and for water the oxidation is 0.23. So our choices in reductions, we want to choose the highest value. Okay, our choices in oxidation, we want to choose the lowest value. Okay, so that will give it you the lowest external voltage. It's going to be negative 83 minus 0.53, which is the best choice. Okay, so again, we've got water being reduced and the other substance, or in this case the iodine, is being oxidized. So the balanced equation is as follows. Okay, we'll do an experiment with this so that you can see various solutions being electrolyzed and you can see the hydroxide being produced or the various substances being produced.